Hello everyone. Welcome to YouTube channel Energy Exergy Theory Applications. I am Tatiana Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. Today, we're with the second law of thermodynamics, and also we will introduce the concept of irreversibility. This is the most difficult discussions always for the students. The second law of thermodynamics is always something like a magic, very difficult to understand. Some people even try to find some philosophical aspects in the second law of thermodynamics. We are the engineers, and we will try to make everything clear and with all possibilities to apply for the energy conversion systems, means for the real world. This is very important for us. And irreversibilities, of course, we also will discuss with the conjunction to apply to real energy conversion systems. The second law of thermodynamics, compared to the first law of thermodynamics, has no one sentence, so definition. The first law, we know this is principle of energy conservation. The second law of thermodynamics has many statements. And usually, always people say that second law is guiding the first law. The second law is not an alternative to the first law of thermodynamics. Both must be applied, of course, and mass balances also. So what is the need for the second law? Why do we need it for the application of energy conversion systems? First of all, with the help of the second law, we can predict the direction of spontaneous processes. So it means that will be introduced some variables that will help us to predict the direction of the processes. This is very important for chemical thermodynamics. Also, we can determine with the help of the second law theoretical performance of the cycle and individual components. As you can see here, I use the word performance. I am not using the word efficiency because, as we already discussed it in the previous our lecture, performance and efficiency, it is not absolutely the same. The word performance can be applied in using the wider spectrum of meaning, but not only efficiency. So I will repeat, with the help of the second law, we will determine the best theoretical performance of cycle and also individual components. We also, with the help of the second law, can find the factors that prevent to achieve the best or theoretical performance of the cycle or performance of the components. And also with the help of the second law, we can establish conditions of equilibrium. Also, the second law of thermodynamic, of course, introduces the absolute temperature scale. This we know, it is also called Kelvin temperature scale, and also it is the set of equations in the limit of the second law will help us to evaluate the properties, thermodynamic properties of working fluids, and so properties that can be measured directly and indirectly means calculated, but this we will discuss later. What is very important for us in all our discussions regarding the second law of thermodynamics, we will use only macroscopic approach. We will not touch microscopic approach. This is different discussions with microscopic approach, and it is not important for us now because we are engineers and we would like to apply to use engineering thermodynamics and apply it for evaluation of energy conversion systems. So let us start with the direction of processes. What means spontaneous processes? And once spontaneous processes are taking place, we need to describe why it happened. For example, we will use the running ball. It is a very simple example coming from mechanics. We have thermodynamic system. Our ball will be the system because whatever we would like to study, it's called system thermodynamics, and we'll move from state 1 to state 2. So, according to the first law of thermodynamics, principle of energy conservation, energy at state 1 will be equal to energy at state 2. Definitely, some contributors will be changed because now we change. will be higher or lower because we change it from state 1 to state 2, but nevertheless, some will be the same. Therefore, we cannot say that spontaneous change in the process associated with moving to lower energy. Energy will be the same. So it means that there are some other factors that will affect to spontaneous processes. Definitely, spontaneous process will be not backwards. So this is mechanics, and now we need to apply all this knowledge on the level of thermodynamics, where, of course, internal energy should be included in our discussions. So if energy of system decreases, for example, or increases spontaneously, it means that energy of surrounding must be increased or correspondingly decreased to the same amount, because energy balance should be fulfilled. So the change in system is equal to change in surrounding if we have energy transfer. So now for us it is not important it is energy transfer in form of work or in form of heat. We have just energy transfer between system and surroundings. So in our discussions, now we always should discuss system and surroundings. This is the biggest mistake when people included to discussion only system and fully ignored surroundings. Please keep in mind surroundings is very important for all definitions. So can we return the system to initial state if system already passed through several processes, for example, from state 1, so I will show like that, from state 1 to state 2. We know that what means reversible process, that system can move from state 1 to state 2 and return with the same trajectory, so repeat the same states from 2 to 1. And sometimes people say that it is reversible process. For system, it is reversible process, but it doesn't mean that for surrounding, it will be also reversible process. And we can make already some intermediate conclusion. Can we return system to initial state? The answer will be yes. We can return system to initial state, but we need special devices that will help us to return system to initial state, and all these devices also should be supplied with energy, because none of the devices will be without energy supply. So example, situation for car drivers, very unpleasant situation. Something happened with tires, and air with high pressure removed to the environment. So from thermodynamic point of view, we can say that is a spontaneous release of pressure from a reservoir with high pressure to surrounding. So from thermodynamic point of view, I repeat, tire will be a thermodynamic system. So yellow, we introduce a system boundary, and change in energy in the system will equal change the energy in surroundings. Now we repair a tire, and how to put air back, so return the system to the initial state. We will use air pump, so the air compressor. This is absolute normal situation for us, but now from thermodynamic point of view, we need to supply work, but it is work associated with surrounding, because this work is not included to the system. So it means that surrounding will be not returned to initial state, only system will be returned to initial state. And now some statements that are together formed the second law of thermodynamics. And all these statements related to direction of the process. The first statement, it is Clausius statement. I will rephrase it using very simple words, that using natural way, heat is always transferred from hotter body to colder body. And as you can see, here is only relative word, hotter and colder, but not hot and cold. So always spontaneous move from hotter body to colder body. Or another statement, that natural transfer of energy from lower temperature to higher temperature is impossible, natural way, but maybe it's possible to do it artificially. And our example is refrigeration machine and also heat pump. So these two energy conversion systems, we discussed it in the previous lecture, that operate according to inverse thermodynamic cycle. So what do we want? What is the goal of refrigeration machine? We would like to transfer heat at low temperature level, which is called refrigeration capacity, to the higher temperature level of the environment. For heat pump, we would like to take thermal energy from the environment and lift the potential to the higher temperature level for heating. Both processes definitely contradict to the second law of thermodynamics, means that natural way is impossible. How to realize these processes in engineering application? We need to supply work. So we need to have special device, and this device will be refrigeration machine and heat pump, and we need to supply energy in form of work from sorting. And immediately this process will be realized for engineering application. There is Kelvin-Planck statement that is first was formulated for the power generation systems, means for heat engine, but we of course can reformulate this also for refrigeration machines and heat pumps. So what do we have according to Kelvin-Planck statement? That for generation of work, that system will operate according to direct thermodynamic cycle and will produce work. We need to have, first condition, two thermal reservoirs, and two thermal reservoirs should be with different temperature levels. So if we have two thermal reservoirs with the same temperature level, work cannot be produced, and for production of for generation of work, better to say, we should have two thermal reservoirs, hotter and colder, or for practical application, environmental conditions and temperature higher than environment. In this way, we can produce work. And now the concept of irreversibilities. So a concept of irreversibilities, it can be, we can say irreversibility or irreversibilities, so singular or plural, depends on how many irreversibilities will be included in discussion for one process, and irreversibilities associated with better to say that it is impossible to return system to initial state using the same trajectory, or system and sorting to initial state using the same trajectories. As we already discussed, system is possible to return to initial state, not always, but possible. So sorting never. So therefore, all processes that associated with how to say impossibility this word to return to initial state for system and sorting simultaneously, all these processes will be for us processes with irreversibilities. I repeat that we will apply only macroscopic approach of thermodynamics. As you can see, I did not mention anything or about molecules, only macro approach. And we have the list of classical irreversibilities, and we always should remember that all these processes are real processes, and we can predict direction of these processes, but we need to proceed further with the second law of thermodynamics. But within all these processes, it is impossible to return sorting to the initial state. So the list of irreversibilities, first five that we will discuss in energy engineering. It is heat transfer through a finite temperature difference, heat transfer with delta T. It is spontaneous expansion of gases or liquids to low pressure. It is spontaneous chemical reaction. It is mixing of matter at different temperatures, different pressures, and different compositions. And also friction of flow of fluids. gases or liquids. And friction, I especially emphasize it on friction because all irreversibilities can be discussed as friction on molecular level. Then we need to apply microthermodynamics. But we already agree, we will discuss only macrothermodynamics. All other irreversibilities associated with electrical engineering and with mechanical engineering, this we will not discuss within our lectures. In all books, and not only written in English language, but also in other languages, irreversibility is divided into two classes: internal irreversibilities and external irreversibilities. Maybe some of you already saw these definitions. Internal irreversibilities usually associated only with the system. So all irreversibilities happen within the system. It is internal irreversibilities. External irreversibilities associated with surroundings, as we already discussed. But we have quite a lot of examples when heat or work is transferred between system and surroundings. In this way, it is not clear definition. It is internal or external irreversibilities. And this really can cause quite a lot of problems with understanding, because it is very arbitrary definition of the system and surrounding. Therefore, I strongly recommend you not to pay attention to internal and external irreversibilities. Let us keep this concept in the past, and we will not focus on this particular words, internal or external. Just we will say we have irreversibilities. And of course, we would like to calculate irreversibilities, because just the word irreversibilities and what we discussed before, everything is only qualitative factors. Okay, irreversibilities are taking place. Because of irreversibilities, we cannot achieve returning the system or system and surrounding to initial state and so on. But we are engineers, we would like to calculate irreversibilities. And I will say very clearly, there is no equation to calculate irreversibilities. Irreversibilities can be described by two values, numerically described by two values. It will be entropy generation or exergy destruction. So please don't try to find equation for irreversibilities, because in many publications, unfortunately even modern publications, the term of exergy destruction just replace it with the letter I as irreversibilities. It is not a mistake, but better to follow very strictly the second law of thermodynamics and all concepts within the second law. Irreversibility, it is only the qualitative factor, and quantitatively we can so it means calculations, we can describe irreversibilities through the value of entropy generation or through the value of exergy destruction. Means we need to proceed with you with the concept of entropy and later with the concept of exergy. And if this lecture was interesting for you and useful, please give a like to this video, subscribe the channel, and share the link with your colleagues. Our next lecture, lecture 5, we will continue with the second law of thermodynamics, and we will discuss the concept of entropy. Thank you.